Hey y'all, we're going to run through our PowerPoint. It's just an introduction to physics and some of the things that we'll be learning in the next couple weeks. So let's get started. This chapter is going to talk a little bit about the scientific method, a really brief overview, a little touch on how physics and society link together, units and dimensions, some basic math which we'll practice in class, and then some strategies for solving physics problems. So physics really is the study of the fundamental law of nature and how things interact in our universe. So the goal of physics is to really get a deeper understanding of the whole world in which we live in. Physics really is everywhere. It's one of the natural sciences that goes along with chemistry, bio, geology, and it's just really an organized way of thinking about nature. Okay, so really brief overview of the scientific method. Remember that it's very systematic. You make observations, you then create a hypothesis of how you think an outcome will come about. You create an experiment and test it. You analyze your data and then make conclusions of whether or not your hypothesis was correct or incorrect, nullified or verified. And both of those outcomes are important because even if your hypothesis is proven wrong, you still gain a lot of knowledge. You can go back and revamp your hypothesis and make a new experiment. We use the metric system because it's the same system that's used globally, and we have to be very consistent so that we can verify people's results that are doing experiments all around the world. The base unit is that unit which talks about the quantity that we're going to be measuring. So for example, length, the base unit for length is a meter. It's abbreviated in meters, little m. The base unit for time we're going to use is the second, which is S. And then the base unit that we're going to use in our problems are going to be the kilogram, and that's kg. All right, so it's called the Système International des Unités. Now, I don't take French, so that's probably butchered. I apologize. So we call it SI for short, and you might hear it called the MKS system, but we refer to it as the SI. Some basic typical lengths for some different things, just to give you a rough idea of how big some of these or how long some of these things are. A football field is 100 meters in length. The height of a person is about 2 meters. And then you can get into some really teeny tiny measurements and some really large measurements. And here we go for mass. The mass is in kilograms, and an automobile, a car, would be approximately 1,200 kilograms, depending, of course, on the make and model. An elephant is about 5,400, whereas a typical human is about 70. Now, keep in mind, we're going to stress this later. There is a big difference between mass and weight. And again, that'll come a little bit later in the course. So for now, just know that when we're making measurements and using them in problems, we're talking about the mass, how much matter is in that object. Mass doesn't change depending upon where you are, and we will see later that weight will. Here are some typical time frames. So if you look here, 1 day has 3.6 times 10 to the 4th seconds in it, whereas your time between your heartbeats is less than a second. Your reaction time, which we'll talk about later as well, is even less. It's only 1/10 of a second. Okay, so if we talk about our metric system, we always talk about prefixes. The example of kilo, it's abbreviated, you put a K in front of it, that's why a kilogram means there's 1,000 grams in it. So 1 kg, kilogram, is 1,000 grams. 10 to the third just means you put a 1 and 3 zeros, so it's 1,000 grams. Also, milli. Now that tells you that it's tiny. It's just a milli of something. And that means it's 1/1000th or 10 to the negative 3. Now there are a whole lot of prefixes, as you can see. Now don't worry. The ones that we really use are the kilo, the centi, and the milli, especially for about the first part of the course. Later, when we get into charges, we'll talk about micro down here, and we'll get this new fancy symbol, but that's much later, so we don't need to worry about it right now. All right, so there's a difference between units and dimensions. Dimensions is actually talking about the physical quantity that you're measuring, or like the type of quantity, whether you're measuring length or mass or time. So when we talk about that, we're just trying to get a grasp on what we're measuring. So what dimensions are you going to use versus the real specifics of how you're measuring that type. Okay, so here's just an example. Like for distance, if we're saying, hey, it's units of length, so there's an L. Or if we're measuring area, well, we know that area is length times width. So it's really two lengths multiplied together. So we say length squared, or volume, length cubed. If we're talking about velocity, we're going to take a distance over a time, so it would be a length over a time. And then we'll see later that acceleration is a length over time squared. But as we use it, it'll just start to become second nature. And in fact, we really focus more on the units really anyway. But it comes into play here when you are trying to convert. So when you try to convert, you need to look at the different quantities so that you line them up correctly. Okay, so converting units from one to another, we'll go over that in class when we do our math review. But if you remember, you have to have a conversion factor. And we'll give you those conversion factors. You'll always have it readily available to you. And for example, 1 meter has 3.28 feet in it. And if you're trying to convert that to meters, you would first set up your given information. So 316 feet, and you can put that over 1. And then you use this conversion factor in the form of a fraction. My stylus isn't working right now, or else I would put this here. But again, we'll go over in class in another presentation a little bit later. But ultimately, you can convert between non-SI units and SI units and back and forth if need be. Okay? Okay, so here's a slide to keep in the back of your head for when we finally do get together and do labs and things together and do analysis. Some sources of error analysis. You can't simply say that we measured wrong, or my lab partner messed it up, or things like that. You actually have to think about what was inaccurate and what things were uncertain. And some of the go-to ones are limitations in your measuring device, limitations in your perception or reading error, and limitations of the skill of the experimenter. All of those things could be used for sources of error in a lab conclusion, but again, we'll get towards that in detail later when we get there. Idea of accuracy versus precision. I know in 9th grade, if you reach all the way back in your memory, we talked about accuracy and precision. Accuracy is how close you get to the accepted value, and precision is how repeated your measurements are, how close together your set of measurements are. And just as a really brief reminder, like if you were playing lawn darts, this here, you have 3 darts that actually hit inside the circle where you wanted to be, so you were very, very accurate, but they were also very close together, so that it was also very precise as well. Out here, they're all close together, so you were precise, but you were really far from your target, so not accurate, but very precise. This one here has good accuracy and fairly good precision. not as good as this one up here. And then this one's just scattered everywhere. You have poor accuracy and poor precision. Okay, a word on sig figs. We're going to go through the rules, but I don't want you to get too hung up on it. We're more concerned about learning the basics of physics than really being stressed out about sig figs. What I don't want to see is an answer that has like 7 digits after the decimal place, because that's just unrealistic. But here we're going to just gloss over and talk about the rules for it. When you measure something, if it has lines, like in increments of 1 centimeter, then you know for sure that something has 2 significant figures if you measure 21 centimeters. But if it's a little bit more, you have to estimate that last one. So the general rule of thumb is that the number of significant figures in a measurement is going to be the number of digits that are actually measured plus 1 estimated digit. When we get back into the lab and we actually get to measure things, we will go over that again. So the general rules for multiplying and divided is that you will take the least number of sig figs for your answer. So for example, if you are going to be using 21.2 divided by 8.5, 21.2 has 3 sig figs. 8.5 has 2. So your answer can only have 2 sig figs. So even if it might come out to 2.571 or 2.531, you would chop it off and round it to 2.5. Again, don't get too hung up on them. As long as you don't have 2.561059, then you're okay. When you add or subtract, it depends on the decimal places. So if you're adding 16.74 plus 5.1, there's 2 decimal places here, there's 1 here. So you can only have 1 in the answer. So 21.8 would be correct and not 21.84. Okay, scientific notation we are going to pay attention to. We'll go over it in class with our math review, but then we probably won't see it a lot until we get into gravitation and charges. Okay, so the general thing here is if you have 2,500 meters, you want to put your decimal place between these first 2 numbers because you want a number that's between 1 and 10. Then what you need to do is you need to count how many places you had to move that decimal to get it back to 2,500. So 2.5, I need to move it 1, 2, 3 to the right so it's a positive. And then we'll go through some more examples. If this were 0.25, and we would put our decimal place here, and you would have to go 1 to the left to get it back the way you had it. So that would be a negative exponent. Alright, so I just want to gloss over graphing. We're going to go into this pretty heavily, probably next week, but graphs are a great way to represent data. You can get a whole lot of information on graphs. So we're going to show you a graph of time and speed. So this graph is going to be speed on the y-axis versus time on the x-axis. Almost always your time will be on the x-axis. Okay, so we have speed here. Whoops. We have speed here and time here. What this graph shows, if you remember from math class, since all the data points lie in this case, a perfectly straight line, usually they're not perfect, you would need a line of best fit, but since they all lie on that line, we say that it's a linear relationship. As x increases, y increases, and they do so at the same rate, and that rate can be calculated as your slope, and we'll go over slope as well. That's different than a parabolic relationship. This is a relationship where as time increases, your position increases faster. So we're going to see that it's more of a squared relationship. Like we say here, x is equal to some number t squared. Okay? But we'll get into all that too. Here, if we have a decreasing line or a decreasing curve, then we know that that's an inverse relationship. As the volume in this case increases, our pressure decreases. Alrighty, so a note on something very, very important in physics, this idea of scalars versus vectors. Scalars have a magnitude only, no direction. Magnitude just means size. So put this definition in there. A scalar is represented by a number and a unit. A vector has a number, unit, and a direction. This is the important part. Vectors actually have directions, and we'll have a lesson on that through the Khan Academy as well. So for example, if you're driving in your car and you're driving at 25 meters per second, that's your speed. Whatever your speedometer says, that is your speed of your car. That is a scalar quantity, because I don't know if you're heading home, heading to school, if you're going to Starbucks, we don't know the direction that you're going in. So if it has no direction, then it's just a scalar quantity. And again, that is a magnitude or a size. If you put it with a direction and you say 25 meters per second north, now we call that a vector. It's a vector quantity because vectors describe both a size and a direction. All right, so some common scalars versus vectors. Scalar quantities, distance. The vector quantity that correlates with that is displacement, and we'll talk about that as well. Your scalar would be speed, your vector association with that would be velocity, and then other common scalars are time and temperature. Another common vector that we will be using is acceleration. That has speed and direction as well. Alrighty. So the best way to learn physics is to do physics. If you skirt out on homework problems, I can almost guarantee that when you get a quiz or a test, you will be really frustrated and you won't really know how to approach many of the questions. So to avoid doing that, you really need to keep up on these problems. Now, the thing is, if you're spending, 4 or 5 minutes looking at a problem and you have absolutely no idea how to approach it, reach out to me on Remind and I can send you a hint to get you started. But once you do more physics, it becomes a lot more second nature. Okay, so we're going to look at some proven methods. You want to read the problem really carefully. So make sure that you know what they're talking about, what they're asking you to solve for. Next, you want to list your given values and your unknown variables. And we'll give examples of these, of course, many throughout class. If necessary, sketch it. We'll get to a section with forces where you'll have to actually make a sketch. For now, though, if you're talking about 2 cars and they're going this way and that way, if it helps you, you can make a little sketch of it. But it's not always necessary. You want to identify and write the appropriate equations. You'll be given an equation sheet. You don't have to memorize them, but you'll be given an equation sheet and you'll have to choose which one would be most appropriate. Then you want to solve it with proper units. And then what you really want to do is you want to check your answer. You want to see, well, does it really make sense? Are my units correct? Does it make sense to say that I traveled to Grandma's house in 2.6 seconds? You want to look at that and see whether or not things make sense and if it's reasonable. Okay, so that's it for that slideshow, just a little intro. We will talk in class. Thanks so much. Bye.